So the next algorithm we're going to look at is a clever idea, not the most efficient algorithm, but it's something called bubble sort. And the idea here is that I'm given a list of elements. I'm going to start at the beginning and compare successive elements. And I'm going to swap them so that the smaller one is always first of that pair. So if I look at the first two and the second element smaller than the first one, I'm going to do the swap. And then I'm going to look at second and third, and then third and fourth. And you can see what happens here. As I walk down the list, I'm basically bubbling the largest element so that after one pass through the list, the largest element is going to be at the end of the list. If I'm lucky, some of the other ones may already be in the right place. But having gone through it once, I can bubble that largest element to the end of the list. I go back and I do the same thing, passing through, bubbling them along. And I'll do that until, in fact, the entire list is sorted. The little animation kind of nicely shows that to you here. You can see how, as we pass through here, bubbling things along, we build up basically that diagonal from this end down. Largest element there first, and then as I go along, the next largest and so on pass through. I might not have to go through the list n times here. If I'm lucky, many of the things might be in the right spot. But in the worst case, you can already get a sense of what the complexity is likely to be. I've got to go through the list, and I've got to do that probably n times. So it's probably quadratic. But let's look at how we might build it. Here's a little algorithm for bubble sort. I'm going to set up a flag that says, initially, I've got a value false, and we'll see why. It's going to let me tell when I'm done. And then I run through a loop that says, as long as I'm not at a true point, while this flag is false, I'm going to let j go from 1 up to the length of list, and I'm just going to compare successive elements. And if in fact I have a case where the element I want to do is bigger than I want, I set the flag to false and I do a swap. And then I go back and do it again. So that inner loop's doing the comparisons. The outer while loop is going to be used for multiple passes until there's nothing left to be swapped. What I'm interested in is what's the complexity of this. And that says basically I have to say how many times do I go through this loop. It could be, in fact, to go down the loop I have to do it n times because I got to look at all of the elements and do the swap. Inside of here there's extra work, which is why it's not as efficient because I've got to do some number of operations, but that's constant for every time through the loop. So I've got an order n, or length of the list, processing here to go through the loop. And then how many times do I do it? If I'm lucky, not very many, but in general it's probably order length n. And so I can see what the order of growth here is. It's n squared because I've got to do n minus 1 comparisons, and I've got to do it n minus 1 times. I can look at a little example of this. I've got a version of a bubble sort on my machine. I'm going to load it in. And what I'm going to do is actually print out what the version of the list is at each pass through the loop so you can see what happens here. And so if I call bubble sort on a little test list, you can see what it does. The first time, when I enter the list is just in some arbitrary order. After I've gone through the list once, you'll notice number 9 is at the end. After I've gone through the list twice, 5, 6, 8, and 9 are all in the right spot. So I got lucky. Some of them happened to be just in the right piece, although what I was really doing was bubbling 8 to its position in the list. And so you see here, I don't actually do this n times, but the complexity is still order n times through the process and order n times within each loop in order to get out the solution I want. So a quadratic solution. Clean little code, not as efficient as I would like.